In the late 19th century, Germany was becoming an industrial powerhouse. The steel and lighting industries had a very practical color of heat problem. How do we know the temperature of molten steel or a light bulb filament just by looking at it? Data was available, but it wasn't quite good for the infrared region. Experimenters like Otto Lummer and Ernst Pringsheim carefully heated their lab-built blackbodies and measured the spectrum of light that came out, and they found a beautifully consistent pattern. When they plotted the brightness of the radiation against its wavelength, they always got the same shape. At any given temperature, the curve would start low for long wavelengths, rise to a peak at a specific color, and then, this is the crucial part, it would fall back down to zero for very short wavelengths. As the box got hotter, the glow got brighter and that peak color shifted towards the more energetic, bluer end of the spectrum. This was the data. A clear, repeatable, well-behaved curve. All that was left to do was to cook up a theory that explained it. For the titans of classical physics like Lord Rayleigh, this should have been easy. They had thermodynamics and electromagnetism on their side. Physicists knew that hot objects glowed and that the color changed from red to yellow, then to blue as they got hotter. But they had no formula to connect temperature T to color, wavelength, lambda. Wilhelm Wien, a brilliant theoretical physicist, approached this not by looking at atoms, which were still controversial, but by treating light like a gas in a steam engine. Long story short, Wien proved mathematically that the peak wavelength is constrained by temperature, i.e. peak wavelength times temperature is a constant. Lambda peak times T equals constant. This is Wien's displacement law. It was a triumph. It perfectly predicted that a hotter star would peak in the blue and a cooler star in the red. Emboldened by his success, Wien tried to guess the formula for the amount of energy at every wavelength, the full curve, in 1896. Since he didn't know about quantum mechanics, he looked at the distribution of speeds in gas molecules, Maxwell, Boltzmann distribution, which looks like e to the power of energy divided by kT. He guessed that light behaves similarly and arrived at a conjecture called Wien's distribution law. At the same time, both Lord Rayleigh and Max Planck had worked at the same problem, figuring out the formula for the amount of radiation energy intensity from a body at every wavelength, the full curve, and they looked at Wien's law, but Rayleigh was not satisfied with that law. He was an older, highly respected expert in acoustic sound waves who looked at Wien's work and essentially said, "This doesn't smell right." Max Planck, on the other hand, loved it but was probably sensing trouble too. He tried to rigorously prove Wien's law and derive it from the first principles. But these principles didn't quite marry together, so in the closing years of 19th century we have Rayleigh and Planck approaching this problem from different sides. In this video we'll focus on understanding Rayleigh's physics and geometry and the terms involved like cavity, modes, and standing waves.
We will follow the logic of 19th century physics off the cliff and see exactly how the ultraviolet catastrophe happens.
It's a story of perfect logic leading to absolute nonsense. But before we break the universe, we need to make sure we speak the language.
And that language is mathematics.
Which brings us to our partner for this deep dive, Alg Prime. Look, we are about to dive into some serious derivation here. We're going to be talking about integers, geometry, partial derivatives, and integration.
It's true. Physics is really just a story written in math. If you don't know the vocabulary, you miss the nuance. You can listen to us describe a partial differential equation, but until you've actually solved one, it's hard to feel the power of it.
That's where Alg Prime comes in. I've been using their platform to brush up on my calculus for this deep dive, and it's genuinely different. It's not just a textbook on a screen.
No, it's interactive. Alg Prime offers tools that help you master everything from basic algebra all the way up to the advanced calculus we're touching on today. They don't just give you the answer, they force you to understand the process.
If you are listening to this and thinking, I wish I could actually follow the derivations step by step with a pencil and paper, you need to check out Alg Prime. Whether you're a student, an engineer, or just someone who wants to understand the language of the universe, this is the place to sharpen those skills.
Check out the link in the show notes for a special deal for our listeners. Get your math skills up to speed so you can spot the catastrophe before it happens.
Ironically, in 1905, with Jeans's corrections to the Rayleigh's thesis, they finally showed conclusively that a hot object should release an infinite amount of energy. Think about your kitchen oven. You turn it on to preheat, and the heating element starts to glow. You might be surprised that according to the Rayleigh-Jeans law, that simple act should lead to a catastrophe. The math, which was considered rock solid, predicted that the moment that element got hot, it should have unleashed an infinite burst of energy, not just cooking your dinner, but vaporizing you, your kitchen, and maybe the entire planet in an instantaneous flash of high-energy light. Yes, the energy dropped off at longer wavelengths. But with higher frequencies and shorter wavelengths, the theory predicted the energy would just go up and up and up forever. The classical approach, building a model. So, how did they get it so catastrophically wrong? Introducing Blackbody. Anything with a temperature above absolute zero is emitting electromagnetic waves. It's called radiation. That means you, right now, are glowing, mostly in the infrared part of the spectrum that our eyes can't see. When an object gets hotter, it starts to glow in colors we can see. Picture a blacksmith pulling a horseshoe from a forge. It starts a dull red, then gets brighter and hotter, shifting to orange, then yellow, and finally a brilliant white. The color of that glow is locked to its temperature. Physicists wanted a universal theory to explain this. And in physics, to understand something complex, you first simplify it. You create an ideal version. Theirs was called a blackbody. A blackbody is a perfect absorber and a perfect emitter of radiation. It soaks up every single photon that hits it and reflects nothing. At room temperature, it would look perfectly, utterly black. Now, nothing in the real world is a perfect blackbody, but you can build something that's incredibly close. Imagine a hollow box with one tiny pinhole. Any light that happens to go into that hole will bounce around inside, almost certainly getting absorbed by the walls long before it finds the pinhole to escape. That pinhole is, for all practical purposes, a perfect absorber. So, a simple concept, blackbody radiation, and if you heat that box, the light that streams out of the pinhole is a pristine sample of blackbody radiation. Its properties depend only on the temperature inside, not the material of the box. The approach was logical and elegant. They decided to model the blackbody as a simple box, a cavity, filled with glowing electromagnetic waves. A resonant cavity is a confined space where waves, light, sound, etc. can bounce around and only certain frequencies can exist stably. Why it's resonant? Because it resonates at specific frequencies determined by its dimensions. The connection to blackbody radiation, the blackbody box is a resonant cavity. That's the physical system being analyzed. Standing waves. They figured the heat from the walls would generate waves trapped inside the box. And what do trapped waves do? They form standing waves. All the others would simply cancel out or decay. The best way to picture a standing wave is to think of a guitar string. When you pluck it, it vibrates in a fixed pattern. The ends are pinned down so they can't move. These are called nodes. The string can vibrate in one big arc, its fundamental note, or it can vibrate in 2 sections, 3 sections, and so on, creating higher harmonics. But the key is, only certain patterns are allowed. The length of the string determines which exact wavelengths can fit. You can fit half a wavelength, 1 full wavelength, 1.5, but you can't fit, say, 0.79 wavelengths. The vibrations are restricted to a specific set of modes. What are modes? A mode is a specific pattern of vibration that can exist stably in a confined space. Think of it as one particular way. Something can oscillate. For example, a guitar string can vibrate in many different ways. As one big arc, fundamental mode, lowest frequency. In 2 sections oscillating opposite to each other, second mode, higher frequency. In 3 sections, third mode, even higher frequency. Only certain patterns are allowed, determined by the boundaries, the fixed ends of the string. This is key. Not all frequencies can exist. Only specific modes are permitted. Rayleigh and Jeans applied this exact logic to the light waves inside their box. Just like a guitar string is fixed at the ends, the electric field of a light wave has to be 0 at the conductive metal walls of the box. This simple rule means that only certain wavelengths of light are allowed to exist inside. They have to fit perfectly. This is where the math starts. Let's make things easy and imagine our box is a cube with the side L. For a wave to exist inside, it has to satisfy the standing wave condition in all 3 directions at once. In the x direction, an integer number of half wavelengths must fit into the length L. We'll call that integer m, so L equals m times lambda x divided by 2. The same goes for the y and z directions. L equals n times lambda y divided by 2, and L equals L times lambda z divided by 2. Each unique combination of integers, m, n, l, n, like 1, 1, 1 or 2, 1, 1, defines a specific allowed standing wave or mode that can exist in the box. Now imagine a 3D grid where the axes aren't x, y, and z, but are mode numbers, n, and l. In this mode space, every point with whole number coordinates represents a real physical wave that can exist in the box. Our problem of counting modes is now just a problem of counting dots on a grid. We first need to connect this to the wave's frequency. You can derive this directly using the geometry of wave components, but there is one critical twist. Wavelengths do not add up like sides of a triangle. Instead, the inverse of the wavelength is what behaves like a vector component. Think of inverse lambda as how many waves fit in a meter, spatial frequency. That is the quantity that obeys the Pythagorean theorem. Here is the step-by-step derivation. Step 1, invert your starting equations. We start with the condition that an integer number of half waves must fit in the box of length L. Now we have the wave density, waves per meter for each direction. Step 2, the Pythagorean theorem for waves. If a wave is traveling diagonally across a room, its total wave density inverse lambda is the vector sum of its directional densities. This is the 3D Pythagorean theorem applied to spatial frequency, y inverses. Imagine a wave moving very steeply, mostly z, direction. It has a tiny lambda z high frequency in z, but a huge lambda x low frequency in x. To get the true small wavelength lambda total, The math relies on the small component lambda z dominating. Using inverse lambda ensures the smallest wavelength contributes the most to the sum. Step 3. Substitute and solve. Now plug in the expressions from step 1, factor out the common term. Step 4. Convert to frequency. We know the universal wave speed equation is c equals f lambda, which means substitute f over c into the left side. Step 5. The final rearrangement. Now, we just move the constants to the left side to get the target formula. Multiply both sides by 2l to the power of 2, combine the squared terms on the left, there is your result. We went from individual directional constraints, MNLL, to the total frequency sphere without even touching a wave number k, so we got this. That's the equation for a sphere. The radius of the sphere, let's call it r, is 2LF divided by c. So all the modes with a frequency less than or equal to some value f must lie inside a sphere of that radius r. Now we can count them. Finding the total number of modes n is the same as counting the number of integer points inside that sphere. Remember the 3D grid with the axes for our mode numbers, n, n, and l. As Rayleigh initially missed, but Jeans later pointed out, we're only interested in the first octant of the sphere because our mode numbers m, n, and l have to be positive. So, the total number of modes n is roughly the volume of that octant, which is 1 divided by 8 times 4 divided by 3 pi r to the power of 3. We can plug our expression for r back in, do a little algebra, and make one final crucial correction. Light waves are transverse. For any mode, the wave can oscillate in two independent directions, or polarizations. So for every mode we counted, there are actually two. We have to multiply by 2. After all that, we did our answer for the total number of modes up to a frequency f, 8 pi vf to the power of 3, divided by 3c to the power of 3. But we don't want the total number. We want to know how many modes exist at a certain frequency. We want the mode density. So, we take the derivative of nf, which tells us how fast new modes are appearing as we increase the frequency. To make it universal, we then divide by the volume v of the box, which gives us the mode density per unit volume, 8 pi f to the power of 2 divided by c to the power of 3. This is our second major milestone, and right here, this is where the disaster takes root. Look at that f to the power of 2 term. It says that as the frequency of light gets higher, the number of available slots or modes for that light to occupy doesn't just increase, it explodes.
You know, it really reminds me of the internet sometimes. You connect to an open Wi-Fi network, and if you aren't careful, your data just radiates out to everyone. There's no boundary condition keeping your private information contained. It just propagates.
That is a dangerous kind of openness.
Yeah.
You do not want your personal data obeying the Rayleigh-Jeans law.
Exactly. That's why you need a filter. You need a secure tunnel. You need our sponsor for this part of the deep dive, NordVPN. Think of NordVPN like a waveguide for your data. In physics, a waveguide is a structure that controls where electromagnetic energy goes. It prevents the signal from scattering all over the place.
That's a great analogy. NordVPN creates a secure, encrypted tunnel. It sets strict boundary conditions on your connection so that prying eyes hackers on the network, your ISP, they can't see the waves of data inside. Your traffic is contained.
And just like a resonant cavity selects only specific frequencies, NordVPN allows you to select where you appear to be in the world. You can route your traffic through a server in Japan or the UK or 90 other countries, effectively changing the mode of your connection to access different content or protect your privacy.
It gives you control over the flow.
It does. So don't let your personal data suffer an identity catastrophe. Secure your browsing and get control. Go to nordvpn.com/deepdive to get a huge discount on your plan, plus 4 extra months for free. It's completely risk-free with their 30-day money-back guarantee.
So we're left with a catastrophe.
Yeah.
Classical math predicts a parabola going to infinity. But experiments, reality, showed a nice, well-behaved curve that goes up, reaches a peak, and then gracefully falls back down to zero at high frequencies.
That peak is crucial. The sun peaks in the visible spectrum in the yellow-greenish range. That's why we see it as yellow. It doesn't peak in the gamma-ray spectrum, thankfully. Something is stopping the high frequencies from taking all the energy.
Actually, when Rayleigh first derived this equation in his initial 1900 paper, he proposed factoring in exponential damping to curb that runaway curve at higher frequencies, because it obviously didn't agree with data and common sense, but there was no way to rigorously justify it theoretically. So what we got so far is the statement that there are way more ways for a high-frequency short wavelength wave to fit inside a box than a low-frequency long wavelength one. But this is just a statement about geometry. It's not the catastrophe. The catastrophe happens when you add the final piece of the classical puzzle, energy, the final piece of the classical puzzle, equipartition. We've counted the parking spots. Now we need to know how much energy goes into each spot. To answer that, Rayleigh and Jeans turned to another cornerstone of classical physics, statistical mechanics, developed by giants like Maxwell and Boltzmann. At its heart is a simple, powerful concept called the Equipartition theorem. The theorem says that when a system is in thermal equilibrium at a steady temperature, its total energy is shared equally among all its degrees of freedom. A degree of freedom is just an independent way to store energy. For a single atom in a gas, it has 3 degrees of freedom moving in the x, y, and z directions. A simple harmonic oscillator, like a mass on a spring, has 2 degrees of freedom, kinetic energy from its motion and potential energy in the spring. According to the theorem, each degree of freedom gets, on average, the same amount of energy, 1 divided by 2 kBt, where T is the temperature and Kb is Boltzmann's constant. So the oscillator's total average energy should be kBt. Rayleigh and Jeans reasoned that each standing wave mode in their box was just like an independent harmonic oscillator. So, in thermal equilibrium, every single one of those modes, no matter its frequency, should have the exact same average energy, kBt. This wasn't some wild guess. It was the direct, logical application of one of the most trusted principles in all of physics. The logic seemed flawless. The box is at a fixed temperature, T. The energy is stored in standing wave modes. Each mode is a degree of freedom. Therefore, every mode gets an average energy of kBt. The stage was set, they had the number of modes, they had the energy in each mode. All they had to do was multiply them together. It should have been a crowning achievement. Instead, it was the beginning of the end for classical physics. The equation in the catastrophe. This is the climax. We have the 2 key ingredients forged from the best classical physics had to offer. First, the mode density, how many modes are available at a given frequency. 8 pi f to the power of 2 divided by c to the power of 3. Second, the average energy per mode from the equipartition theorem. Average energy per mode equals kBt. To get the energy density, or the energy per unit volume at a given frequency, we just multiply them. And there it is. This is the Rayleigh-Jeans law. This is the equation that predicted infinite energy. It's a simple, elegant formula derived from first principles. There are no fudge factors. It is the logical conclusion of 19th century physics. And it was an absolute spectacular failure. Here's why. At very low frequencies, the equation actually worked beautifully. It matched the experimental data almost perfectly. They must have thought they were so close, but as you go to higher frequencies, the 2 curves diverge. While the real-world data shows the energy peaking and then falling back to 0, the Rayleigh-Jeans law just keeps going up. Because of that f to the power of 2 term, as frequency f gets higher and higher, the predicted energy shoots up to infinity. This is the ultraviolet catastrophe. The name, coined later in 1911 by Paul Ehrenfest, was perfect. The theory predicted that any hot object should be blasting out an infinite amount of energy, mostly in the high-frequency ultraviolet range. If this were true, lighting a match would release enough energy to sterilize the planet. The simple fact that we exist proved that the Rayleigh-Jeans law and the physics it was built on was deeply, fundamentally broken. But the timeline of events was so bizarre that by the time Rayleigh and Jeans rigorously showed what kind of crisis this logic led to, the paradox was already solved by German physicist Max Planck in 1900, who was deeply at work tackling the problems of Wien's distribution law. Problem 1 was trying to rigorously derive it from first principles, and problem 2 was to reconcile it with the latest experimental data for the infrared zone that arrived in 1900. Experimentalists like Rubens and Kurlbaum had better and better data showing that at low frequencies the curve was proportional to temperature T, not what Wien predicted. At low frequencies, infrared zone, the data was in favor of Rayleigh formula actually. The resolution, a quantum leap. Planck was a conservative physicist. He didn't want to break physics, he wanted to save it. For years he tried to find a flaw in the classical derivation, some way to make it fit the data. He couldn't. He resorted to Boltzmann's statistical methods and atomism. So, in 1900, he decided to try something that made no sense. He decided to cheat. He realized that to make the math work, he had to make a bizarre assumption. Classical physics assumed that energy was continuous. An oscillator, one of our standing wave modes, could have any amount of energy. It could have 1 unit of energy, or 1.115. Energy was a ramp, you could stop anywhere. Planck's desperate idea was to throw that away. He proposed that energy is not continuous. It is quantized. He suggested that an oscillator with a frequency f can't just absorb or emit any random amount of energy. It can only do so in discrete packets, or quanta. And the energy of one of these packets, he proposed, was directly proportional to its frequency. In an act of quiet desperation, he wrote down one of the most important equations in all of science. E equals hf. E is the energy of a single packet, f is the frequency, and h is a new fundamental number, now called Planck's constant. This idea was revolutionary and deeply weird. It meant energy isn't a ramp, it's a staircase. You could stand on the first step, or the second, but you can never stand between steps. Energy only comes in chunks of hf. So how does this crazy idea fix the ultraviolet catastrophe? Brilliantly. Think about our standing wave modes again. A mode with frequency f can't be energized with just any tiny amount of heat. To get switched on at all, it has to receive at least one full packet of energy, E equals hf. For low frequency modes, that packet is very small. The thermal energy available in the oven, kVt, is easily large enough to create these cheap packets, so those modes get energized just like classical physics predicts. That's why Rayleigh-Jeans works for low frequencies. But what about the high frequency modes, the ones in the ultraviolet? For them, the frequency f is huge. That means the price of admission, the energy hf of a single quantum, is enormous. At a given temperature, there just isn't enough energy bouncing around inside the box to create these incredibly expensive high-energy quanta. The high-frequency modes are effectively frozen out. They exist as possibilities, but the cost to turn them on is too high. The energy isn't shared equally. The expensive high-frequency modes get almost nothing. This forces the energy curve to peak and then fall back to zero, perfectly matching the experimental data. Using this idea, Planck derived a new formula, now called Planck's law. This equation was a complete triumph. It perfectly described the blackbody spectrum at all frequencies. For low frequencies, it even simplifies into the old Rayleigh-Jeans law. At first, Planck himself was very uneasy with his idea. He thought it was just a mathematical trick, not a description of reality. He desperately tried to justify it and get the physical ground for his quantum formula that made up introducing the H factor, but the genie was out of the bottle. Soon enough, others took Planck's quantum idea and argued that it wasn't just oscillators that were quantized. Light itself was made of these packets, these photons. And that's when the quantum revolution truly began. Conclusion. The story of the Rayleigh-Jeans law is a perfect parable for how science really works. It started with confidence, even arrogance, that we had it all figured out. It proceeded with a beautiful logical theory built on the strongest foundations they had. And it climaxed in a spectacular failure. A catastrophe that proved our understanding of reality was wrong. The equation that predicted infinite energy wasn't just a mistake. It was a signpost, pointing from the world we thought we knew to a much starker, deeper reality. The ultraviolet catastrophe was the crisis that made deeper inquiry necessary. By trying to solve a simple puzzle about why hot things glow, physicists resorted to the idea that maybe energy itself is grainy, that light comes in particles. It is, without a doubt, the most productive wrong turn in the history of science. Here are brief biographies of the two British physicists whose names are forever linked by their famous formula. Lord Rayleigh, John William Strutt, 1842-1919. John William Strutt, known as the third Baron Rayleigh, was one of the giants of classical physics. A British aristocrat who preferred the laboratory to the House of Lords, he possessed a rare combination of mathematical brilliance and experimental precision. The Nobel Prize. He was awarded the Nobel Prize in Physics in 1904 for the discovery of the element argon, which he isolated with William Ramsay, proving that the atmosphere contained gases previously unknown to science. Why the sky is blue, he formulated the theory of Rayleigh scattering, which explains how light scatters off molecules in the air, giving the sky its blue color. Sound and Waves, his two-volume work, The Theory of Sound, is still considered a foundational text in acoustics today. The formula, in 1900, he applied the Equipartition theorem to radiation inside a black body, deriving the relationship that predicted the energy output at low frequencies. He was the Cavendish Professor of Physics at Cambridge, succeeding Maxwell and a mentor to J.J. Thomson. He represented the pinnacle of 19th century classical physics, Sir James Jeans, 1877-1946. Sir James Hopwood Jeans was a mathematician, physicist, and astronomer who belonged to the generation following Rayleigh. While Rayleigh was the experimentalist, theorist, Jeans was a pure applied mathematician who turned his focus to the cosmos. The correction, in 1905, Jeans found a numerical error in Rayleigh's original blackbody calculation. He corrected the constant of proportionality, solidifying the equation now known as the Rayleigh-Jeans law. Astrophysics, he made massive contributions to stellar dynamics. He defined the Jeans mass, or Jeans instability, which is the critical mass required for a cloud of interstellar gas to collapse under its own gravity to form a star. Cosmology. He engaged in famous debates with Arthur Eddington regarding the formation of the solar system and the nature of stars. The great communicator, in his later years, Jeans became one of the most famous popular science writers in the world. Books like The Mysterious Universe, 1930, introduced the public to relativity and quantum mechanics. He is famous for his philosophical quote, "The universe begins to look more like a great thought than like a great machine." Of course, the story doesn't end there. Let me know in the comments what mystery you think we should tackle next. And if you enjoyed this trip to the edge of classical physics, consider subscribing and watching my other long-form videos all the way through and checking out NordVPN, AlgePrime, MatParse, TubeMagic software, and VidAI, and all the other products I recommend. Thanks for watching.